Guys, are you there? Hello?
Hello.
Yeah, we're here.
Hey, so I'm having some problems. My iPad is not working. So I'm gonna try to fuck around with the Wi-Fi and see what happens. Oh, I see the problem. Hey, could somebody stop? Could you guys mute yourselves? Somebody's making a lot of noise out there. Okay. Turned out my computer was hooked to the wrong network and my iPad was on a different network and I had to get them synced up. Okay, so guys, can you hear me? Can you hear me okay?
Yes.
All right. Okay, so so let's see, I just lost 3 minutes. So I guess I'm going to go a little over in this lecture, and if you have to leave early, if you have to leave, just leave, and you can look at the recording, but I just lost 3 minutes on this bullshit, so I'm gonna go over. Okay, so today the issue is, or the thing that we're going to talk about is the main topic for today is addition of angular momentum, or actually addition of spin angular momentum. And this is an important topic, and you guys have already maybe you've done some addition of angular momentum in the past, but this is I'm not sure if you have or have not, but this is important for when we have multiple particles. And so this is all part of this discussion that we're having about many-body quantum mechanics of many particle systems. So so let's just remind ourselves a little bit of where we're at right now. We've been talking about many-body states, and we've talked about symmetrization, and we saw that the many-body wave function can be written as a Slater determinant. And I'm just going to, for shorthand, I'll just write it like this. So if I have some single particle states, A, B, C, up to say some, arbitrary state C, then if I can make a determinant by having state A of particle 1, I can put particle 2 into it, up to some C, for the nth particle, and then I can do the same thing for all the states, and I can construct this weird Slater determinant, which gives me a symmetrized wave function. It's a symmetrized many-body wave function. And so that's a mathematical trick, which is very useful. And so then we talked about for two particles, then if I put two particles into a box, here's my box, and I have state A, B, C, etc. If I put both of the particles, one in state A and one in state B, and suppose these states have well-defined energies, they're single particle states, but now I'm going to construct a many-body wave function out of the single particle states. So just so you understand that that's the recipe. We start with the single particle states and we construct our many-body states out of them. Then we see that there's 3 different cases. If I have distinguishable particles, then I can write my many-body state as just psi A of particle 1, put particle 1 into psi A, and I can put particle 2 into psi particle into state B. And this has energy A plus B, epsilon A plus epsilon B. Or I could have indistinguishable fermions, in which case I see that the wave function is going to be, and I can construct this using the Slater determinant. It's going to be, I put particle 1 into state A, I can put particle 2 into state B, but then I also have to consider the possibility that particle 1 is in state B and particle 2 is in state A. That's why I add these possibilities up. And then I have my, and so this is, it has the same energy, but this has no symmetrization, and this is anti-symmetric. And then I could have indistinguishable bosons, in which case I have the same wave function. I won't write it all, just the same one, but now I put a plus sign here and it's symmetric. Now these are wave functions for, there's no interactions between the particles for these wave functions, and they all have the same energy, but the physics is different. Physics is different. And the physics is different, and we talked about that last time. What makes the physics different is that the fermions are farther apart spatially. They're farther apart in space. We proved that. And the bosons are closer. They're literally closer to each other. And we figured that out by calculating this quantity, the distance between the 2 particles. The expectation value of this told us that. So that's pretty cool. And so then I was going to tell you about a physical consequence of this. And I was going to, and I mentioned that this leads to magnetism, the phenomena of magnetism that you all know. It's how you stick things under your refrigerator. And so I think I just want to mention that because that leads us then to the next topic, which is spin. So that leads us to the topic of spin. So in order to see how this symmetrization leads to magnetism, it's not too hard. Let's first consider spin. Now we have to talk about spin, and let's consider one particle. And you've done this before. This is review. You know that if I have a wave function of one particle, then that wave function can be written. If I want to include spin, I can write it as a spatial part times a spin part. And so that's the spatial wave function, and that's the spin wave function. And it's a product. And that's an easy thing to do, and it sort of should make sense because what's happening is I have 2 properties at the same time, 2 simultaneous properties. I have space, I have my spatial probability, and I have my spin probability. So when you're talking about the probability of 2 things, then that naturally leads to a product. Because you all learned in high school or somewhere that when you're talking about simultaneous probabilities, you multiply the probabilities. All right, and the wave function is all about probability. So I just want to remind you that. That's just a basic part of quantum mechanics. But so now let's talk about many-body states with spin. And now we would say, now we can just generalize this concept, because now we have the many-body wave function of a system of multiple particles, MB for many-body. And now I can just write this, I can just write it as a product of the spatial part. Let's say that there's n particles times the spin part. And so I'll just call that S1, S2, S3, Sn. Okay, so this is the many-body, this is the spatial part, the many-body spatial part, and this is the many-body spin part. So I just multiply the wave function. So it's just a very sort of straightforward generalization of the single particle case. But now for the many-body, we have to consider, we need to symmetrize it, right? We need to symmetrize these wave functions. And so we can consider, we then have to remember, we have to then consider the symmetrization of the different parts, because we now have to ask ourselves, what happens if I hit the spatial part of the wave function with the exchange operator? Is it plus or minus? What's the symmetry of the spatial part? And I can also ask, what's the symmetry of the spin part? Right, I can, because they can each have a symmetry under particle exchange. So we can construct them so that they are symmetric. And we've already been, what we were talking about before is these states are spatial. So we've only been talking about the spatial, these are spatial states, but we can also talk about spin states. And so that means then that we can consider the, so now if I have a many-body state and I want to consider what happens under particle exchange, then I have to know what is the symmetry of the spatial part times the symmetry of the spin part. And so we can make a table, because they can be either, because they can be either plus or minus. They can be either symmetric, which I'll represent with a plus sign, or anti-symmetric, which I'll represent with a minus sign. And so we can construct a table, and the table looks like this. I can construct the table like this, and I can see that my total wave function is going to be, it's going to be the product of my spatial wave function times my, I'll write like this, my spin wave function. And the symmetry of the spatial wave function can be, suppose the symmetry of the spatial wave function is plus, and the symmetry of the spin wave function is plus, then what is the symmetry of the total? What is the total symmetry of the total wave function? And so basically what I'm asking you is, if I exchange two particles of my total wave function, which is the product of the spatial part times the spin part, what is the symmetry of that? That's going to equal the same thing, but it will be plus or minus. Which one is it? So if the spatial wave function has plus symmetry and the spin wave function has plus symmetry under particle exchange, what is the total symmetry of the entire wave function? That's a question I'm asking you.
Plus.
Right, because it's a product. It's just this times that, so it's plus. Another possibility is that the spatial wave function has negative symmetry and the spin wave function has negative symmetry under particle exchange. It means that they get a negative sign when I do the exchange. In that case, what is the total symmetry of the total wave function?
Symmetric.
Say it again, what?
Symmetric?
Well, yeah, plus or minus. That's what I'm asking, plus or minus.
Plus.
Exactly, because minus times minus is plus. Good. Now, another one is that the spatial part could have negative symmetry and the spin part could have positive symmetry, in which case the total symmetry is what?
Minus.
Exactly. This is not hard. Then the spatial part could have plus symmetry or the spin part could have minus symmetry, in which case the total, again, is minus. Okay, so these are all the different possibilities that we could have for the total many-body wave function, including space and spin. But now I'm going to ask you a question. For a system of fermions, like electrons, for indistinguishable fermions, the nature chooses one, only one. Which one is it? There can only be one. It's like the Highlander. So which one does nature choose? And I'll name them. I'll call this one 1, 2, 3, 4. So I'll ask you, can it be number 1? Could nature choose case number 1, this one? Yes or no? Why?
No.
And why?
Since fermions need to be antisymmetric.
And is this one antisymmetric?
No.
No.
That's right, because it's the total that matters. This is what matters. It's the total symmetry, and the total symmetry here is plus. How about case number 2? Can nature pick that?
Nope.
That's right. So that gets an X. This one gets an X. How about number 3? Could nature pick that one?
Yeah.
It could.
Yeah.
So that gets a little star. How about number 4? Could nature pick that one? Yes or no?
Yes.
Good. That's right. So the last 2 are possible. Nature could pick them. But as I said, nature only picks one. So if the particles have no interactions, like they don't feel each other, then nature is not going to pick between those 2 cases because they have the same energy. And so nature doesn't care. They're degenerate. But let's turn on Coulomb interaction. They're electrons after all, they have charge. Turn on the Coulomb interaction and now the particles can feel each other. And so now, because of the Coulomb interaction, nature picks one of those 2 states. Is it 3 or is it 4? And why?
I think 3 may be more likely because Coulomb interaction will push the particles with the same charge away. And
that's right. That's exactly right. So this is the one that nature chooses. And the reason is just what you were saying, which is because for it's what we just proved last time. For the antisymmetric spatial case, then the particles farther apart. And when the particles are farther apart, if they have charge, then that means their energy is, I'll ask you, is it higher or lower? Is the energy higher or lower for charged particles when they're further apart?
lower.
Lower.
Exactly. And that's why nature likes it, because nature always likes to go to the lowest energy state. And so that's the one. Energy is lower. And so that means that the spin part has plus symmetry. But what does it mean for the spin part to have plus symmetry under particle exchange? That means that we need to understand this. We need to understand the many-body spin wave function. And that leads us to the next topic, which is what we're going to discuss, the many-body spin wave function. But before getting into all the details, I just want to finish this point before getting lost in all the details. The point is simply that, let's consider many-body spin wave function. The simplest many-body spin wave function is just a product state. All right, the simplest is just, if I have, let's say, 3 particles, I could just say, I would just say I have spin 1, spin 2, spin 3. So that's the simplest many-body wave function, the same that we did for space. Remember, we just multiplied the single particle wave functions together. So the simplest many-body wave function is just a product state. Now, if the particles are indistinguishable, that means they have the same spin. So really, I shouldn't say S1, S2, S3. I should really say M1, M2, M3, because that's the spin, right? It's the Z component, because they all have the same spin if they're electrons, spin 1/2, but they could be either up or down. So, so let's take a look at this. So now let's consider this spin wave function up. Consider this spin wave function up. Now, this is particle 1, this is particle 2, this is particle 3. So if I exchange, and let's consider that one. So now if I exchange any two particles here, is it symmetric or anti-symmetric? Is it symmetrized? Someone tell me. Is it?
Yeah.
Is it symmetric or anti-symmetric?
Symmetric.
Exactly. So this is symmetric. But how about if I had chosen this one? Up, down, up. Is this one symmetric? This is particle 1, particle 2, particle 3. If I exchange particle 1 and particle 2, do I get the exact same state?
No.
That's right. Is it symmetrized? Yes or no?
It's not symmetrized.
That's right. So which one does nature like? This one A or this one B?
A.
Yes, nature wants A. Okay, look at that. Notice that the physical characteristic of that state is that all the spins are pointing in the same direction. When spins point in the same direction, we have a name for that. What do we call it when spins are all pointing in the same direction? Can someone tell me? What do we call that?
Is it like
symmetric?
What?
Symmetric?
Yes, it is symmetric, but there's another name. What did there's a name that you knew even before you learned any quantum mechanics.
is it like maximum multiplicity?
I don't know. Actually, I'm not sure what that is.
As in like Hunds rule? Or
It is Hunds rule. It is Hunds rule. But I don't know if that's the word I would use, maximum multiplicity. There's another word I want to use.
Is it magnetic?
Yes, we call this magnetism. That's what magnetism is. Things are magnetic when the spins are all pointing in the same direction. That is magnetism. That's what it is. I mean, you know, that's just what it is. Okay, so that's the end. So that's the whole point, is that this anti-symmetrization of the wave function led to this low energy state where all the spins are pointing in the same direction. And that is magnetism. And another word for that, which you mentioned, is Hunds rule. This is also called Hunds rule. So what we just did was we just sort of derived Hunds rule in sort of a hand waving way. Okay, well all right, so this very naturally then leads us. Yeah.
I just had a quick question. So you said that the requirement that the spins be symmetrized is a result of the fact that because of Coulomb interaction, particles which are farther apart will have lower energy. So what if we have fermions which have spin but no charge, like a neutrino or something?
Fermions that have spin but no charge.
Yeah.
That's an interesting concept. Can you give me an example of one?
I think the neutrino.
Yeah. Okay, the neutrino. Yeah. So then this would not work.
So for neutrinos, they can have states with symmetric spatial wave functions and antisymmetric spin wave function.
I mean, you know, the anti-symmetrization has to occur, and so the whole point of this conversation was that of these, this table of these four possibilities, the Coulomb interaction made possibility number 3 more likely. Nature chose that because it has lower energy. If I had neutrinos and there's no charge, then that means that there's no difference energetically between state 3 and state 4 on this table that I'm showing you here. But the neutrinos would have to choose either 3 or 4 if they're charge neutral fermion. You know, if there's fermions, they got to be antisymmetric. So they would choose either 3 or 4. Okay, does that make sense?
Yeah, so both of them would be equally likely to be chosen?
Sure. Yeah. There's no energetic distinction. That's it. That's the only thing. So that's what. And so the point is, magnetism is driven. Magnetism is a funny thing because you always think of it being driven by the spins, but it's actually driven by the Coulomb interaction. It's the Coulomb interaction that is the energetic driver of magnetism. And the spins are just along for the ride because they determine the symmetrization of the wave function. Yeah. So it's sort of a very cute little thing to notice. Okay, so now this is bringing us into this whole discussion of spin. And so let's continue to discuss spin. And so now I want to sort of shift gears a little bit and let's have a general discussion of the many-body spin states. General discussion of many-body spin states, okay? And this is going to lead to addition of spin. Addition of spin. So, okay, so what we're going to do is, let's suppose that we have, let's consider we have n particles with spin. And we ask ourselves, what's the simplest way to construct the many-body spin wave function? And so there's different ways that we could do it, but the simplest thing is always to create, well, I said it before, can someone tell me what's the simplest thing to do?
Type them together.
A product state, that's right, it's a product state. So the simplest thing is to just say, well, I got the spin state of particle 1, and I got the spin state of particle 2, right? And I got the spin state of particle 3. And I just will keep multiplying them out until I get to the very last one. And that's a product state. And that's the simplest thing to do. And now we can ask ourselves, what does this mean? What is it that we have constructed? What is a product state? And a product state really is basically what we've done without even thinking about it, is to construct it's a simultaneous eigenstate. It's a simultaneous eigenstate of these operators. I'm going to have S1 squared, S1z, right? And I also have S2 squared, S2z, and on, to Sn squared and Snz. And these are operators. And all of these operators commute with each other. They all commute. And that's why I was able to construct a simultaneous eigenstate of them, because you remember that from last semester. To construct a simultaneous eigenstate, the operators need to commute. So they all commute, and so that's what the product state is. It's a simultaneous eigenstate of all those operators. But you guys, but now let's suppose we have spin. Let's do spin 1/2. Consider we have spin 1/2 particles. Then we know that for each case, there's for each particle, how many states are there for each particle? What?
2.
Yeah, up and down. And so for spin 1/2 particles, we have 2 states for each particle. And so we have this one would be 2 states times 2 states times 2 states. And so we see that for n particles, there's 2 to the n states. Okay, so there's a whole bunch of, this is the number of possible product states. So we have all these product states. We have 2 to the n of them. Now, the way to think about it is that this creates, the way to think about it is that this creates a vector space having 2 to the n elements. In other words, the dimension of the vector space is equal to 2 to the n. That's the way to think about it. So now what we're going to do is we're going to shift gears and we're going to think about it all in terms of linear algebra. because as I said before, the natural language of quantum mechanics is the language of linear algebra. And I just want to be very clear, the language of quantum mechanics is not analogous to linear algebra. The language of quantum mechanics is literally linear algebra, one and the same thing. Okay, so, because I remember when I was learning quantum mechanics, I was learning all this stuff and I remember thinking, wow, that really looks a lot like linear algebra, but then, but that was before I actually had learned a lot of linear algebra. Then as I learned more linear algebra, talking about adjoints and all that stuff, I was like, oh my God, it's all the same. So I just want to be very clear. The language of quantum mechanics is literally one and the same, the language of linear algebra. So all your linear algebra knowledge can be applied directly to quantum mechanics. And I hope you have some. If you don't, and you want to know more about quantum mechanics, go get some. Okay, so let's talk about linear algebra. So this vector space, of course, in quantum mechanics, we call it the Hilbert space, but it's really just a vector space, all right? Okay, so for n particles, we have this, 2 to the n dimensional vector space. And the point that I want to make is that these product states, are we can think of the product states that I just mentioned. The product states form a basis, meaning that it's a basis for this vector space, meaning that I can write any state in the vector space as a linear superposition of these product states. They form a basis for the vector space. But an important point that I want to make is that other basis states are possible. Other basis states are possible. And so what we did is, the simplest case is the product states. And the product states are simultaneous eigenstates of these guys, S1 squared, S1z. How I want to write this? Like a really simple point I'm trying to make, but as you try to get it all perfect, it gets harder and harder. But S2 squared, S2z, etc. So that's what the product states are. They're the simultaneous eigenstates of these operators. But I can create other basis states of spin. How do I create other basis states? And this is just linear algebra. Because remember, in linear algebra, the basis states of some vector space, you construct basis states out of eigenstates. Eigenstates are what give us the basis states. You can pick eigenstates of one operator or eigenstates of another operator, and that gives us new basis states for the same vector space. So one possible set of basis states for all my spin states is the eigenstates of these operators, S1 squared, S2 squared, S3 squared, S1z, S2z. What's another possible set of basis states to describe my spin wave functions? Can you guess?
Can we possibly do it in the x direction?
Well, that's a good guess, because that's a different operator, right? You said x, and so it's a different operator, so that's the right way to go. You got to find a new operator, but x is not quite the right one because that's space, and spin has nothing to do with space. So we're just talking purely about spin. So there's no space here. It's just spin. So we need to find the eigenstates of a new operator to give me a new set of basis states. And so I'm asking, what is that new operator? What?
How about the Hamiltonian?
Yeah, the Hamiltonian, but the Hamiltonian is very specific to every single case. So the Hamiltonian is a little too specific, because the Hamiltonian also has potentials, it has spatial components. Now, this is even simpler than Hamiltonian.
Is it angular momentum?
Yes, it is, but what kind of angular momentum? I mean, we're talking about spin angular momentum, not orbital angular momentum. Remember, this is all spin.
Like the total spin for the system?
That's it. Bingo, you got it. Because the old operators that we diagonalized, old operators, are this: S1 squared, S1z, S2 squared, S2z, 2z, oops. All the way to Sn squared, Snz. That gave us the product states, but the new operators that we want to diagonalize is this, S total. And S total is a vector, and it's equal to S1 plus S2 plus S3 plus Sn. And what we want to do is we want to find the eigenstates of this operator. And those eigenstates are going to give us, it's a new set of eigenstates, and those eigenstates are going to be called this. They're going to be called S total Z, and this new set of eigenstates is going to form a new basis. And this new basis is going to be that is what it means to add angular momentum, or add spin angular momentum. And the new operator is S total, and it's also going to be S total Z equals S1Z plus S2Z plus S3Z, etc. to NZ. So what I want, so the point I'm trying to make now is that when we talk about, because the language is really weird, you know, when we're talking about, like when you're talking about adding angular momentum in classical mechanics, you're literally adding, you know, these vectors, you're adding, you know, this physical angular momentum. But in quantum mechanics, when we talk about adding angular momentum, what we're really doing is we're converting from one basis to another basis. So that's the point that I want to make. Addition of spin is the same as a basis conversion. It's a conversion from one basis to another, basis conversion. We're converting from the eigenstates of this set of operators, S1 squared, S1z, blah, 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 to Sn squared, Snz. We're converting from this basis, from the eigenstates of this set of operators to the eigenstates of this set of operators, S total squared, S total Z. All right. So it's a conversion from these eigenstates of those operators to the eigenstates of these operators. Okay, so that's what we're going to do. We're going to convert from one set of eigenstates to another set of eigenstates, and that is addition of the angular momentum. So I really want to get that point across. Okay, so now let's consider. So let's talk about this new operator. Let's consider the properties of this new operator. S total equals S1, S2, etc. So this is the spin. So the total spin operator is just an addition of all the spin of all the different particles. We just add them up. But then it turns out that we can define. So now let's define the total spin squared, and the total spin squared is just S1 plus S2 plus Sn dotted into S1 plus S2 plus Sn, right? And that's the definition of S squared. You know, it's the same as the classical definition. And then we can also define S total Z, which is just going to be the sum of all of the Z component, right? Of all the of the spin of all the particles. And so now let's start. So now we've defined these two new operators, S total squared and S total Z. And what we can notice is that if we want to understand the states, we want to understand the eigenstates of these new operators. And in order to understand the eigenstates in quantum mechanics for angular momentum, how do you understand the eigenstates? What is it that determines all the properties of the eigenstates of angular momentum? I've just defined the operators of angular momentum. I can also, of course, define S total X, right? Equals, the sum of all the X components. And I can also define S total Y. I might as well do that, right? The sum of all the Y components. But now that I've defined the operators, how do I understand the properties of the eigenstates from the operators? What is it that allows me to understand the properties of the eigenstates? Can anyone tell me?
Is it the eigenvalues?
The eigenvalues are very important, and every eigenstate has associated with it an eigenvalue. So you're right. Understanding the eigenvalues is implicit in understanding the eigenstates. But I'm looking for something different. If I've just defined a set of operators for you, and now I'm asking you, how do I understand both the eigenstates and the eigenvalues? What is the key mathematical property of these operators that determines all the properties of the eigenstates and their eigenvalues? What is it?
Are they Hermitian?
Well, it's like we're sort of assuming that they're Hermitian because every physical observable in physics is Hermitian because we need, for the reasons that you learned last semester, you need real eigenvalues to be measurable, etc. So we're sort of working under the implicit assumption that they are Hermitian. So I'm looking for something different.
See if they commute.
What?
Yeah, see if they commute.
Yes, that's it. Thank you. The commutator. That's right. It's the commutator. And it's sort of a trick question because, if you would have to remember the discussion because you guys did this last semester when you did orbital angular momentum, and you remember you did the raising operators and the lowering operators, and you did all that, orbital angular momentum, and it was all very confusing. But hopefully now it sort of makes sense. That's right. All the properties of angular momentum come from the commutators. That's the starting point. And so to understand the eigenstates, we need to understand the commutators. And everything comes from them. And so we then ask ourselves, what are the commutators? S total squared, S total Z. Okay. Now, if I took off the, if I took off the little t, the total, and if this was just like regular spin of a single particle, what is the commutator of S squared and SZ? What is it?
0.
That's right. But now I'm talking about the total. So what do you think it is now for the total spin? What do you think it is? What do you think it is?
Still 0?
Yeah, exactly. It's still 0. And I'm not going to prove that to you. Go off and prove it yourself. I think that's in the homework. Okay, so go prove that to yourself, because it's just some tedious little math proof. Multiply it all out, and so you prove that that's in the homework. But the point I want to make is that the commutators is exactly the same, and I have S total X, S total Y is equal to IH bar S total Z. The commutator structure of the point I want to make is that the commutator structure of the total angular momentum operators is exactly identical to the commutator structure of the normal angular momentum operators. So it's the same as regular angular momentum. And what that means is from the commutators, then you construct the whole algebra of angular momentum. What if the commutators are the same? That means then that we can define. That means then that we can define. It means that we can define simultaneous eigenstates of S total squared and S total Z. The eigenstates are. We can define the eigenstates S total M total, right? Where now there's so this is an this is a simultaneous eigenstate of S total squared and S total Z. And also we can define, just like before, we can define raising and lowering operators. I can define S plus is equal to Sx plus, I have it written down, I want to make sure I don't screw this up. Yeah, I can do, let me write this correct so I don't screw up my notation. I can define S total plus is equal to S total X plus I S total Y, and I can define I can define my lowering operators. S total minus is equal to S total X minus I S total Y. And then we know that, and this is exactly what you guys already did. That's why I can just blast through this, you know, even though you might not remember it too well. I know you remember that you once understood this, even though, you know, you might not have it all in your minds now, but this is the logic that you went through last semester. And so the point I want to make is that once you define the total angular momentum operators, they have all the same properties as the individual angular momentum operators. And so everything you did with the normal angular momentum operators, you can do it all over again with the total angular momentum operators. And it all works. And proving that will be part of your homework. But now I'll just remind you that, you know, if I hit if I hit like an S total, M total simultaneous eigenstate with the raising operator, then it's gonna, well, what's it gonna do? Somebody tell me, you know, if you hit a state with the raising operator, what does it do to the angular momentum state?
It raises the angular momentum by like one integer.
Exactly, but which angular momentum? Which part of the angular momentum?
The M part.
Exactly, the Z component. Good, that's exactly right. So, and then there's some details of the math. You know, there's an H bar, and then there's some little nuances here that you guys all worked out, and you could work it out again. It's S total plus 1 minus M total plus 1, you know, the little normalization constant that you guys all worked out last semester. It's the same here, and this is M total plus 1. I ratcheted it up. And the same thing is, I can define my minus 1's S total, M total is equal to H bar. And for going, this ratchets me down, S total plus 1 minus, that's the same, but then the minus sign is right inside here, minus 1, S total, M total minus 1. Okay, so you guys did all this last semester. And then when you go through all the screwing around with these raising and lowering operators and all the various little clever mathematical arguments, you can prove that S total squared acting on the simultaneous eigenstate of total angular momentum is going to be equal to H bar squared times something times S total, M total. This is the eigenvalue. It's the constant. What is it? Someone tell me. H bar squared times what?
ST times ST plus 1, I think.
That's right. Exactly. And by the same reasoning, you can show that STZ acting on, and these are operators, acting on this eigenstate is equal to H bar times what? Times the eigenstate. H bar times what?
The square root.
No, because this operator, the Z component operator hits the eigenstate.
Yeah, M, then M.
Exactly, M total. Where the value of M can be greater or equal to something or less than equal to something. It's greater or equal than what?
Negative S.
Exactly.
ST, I guess.
Very good. And it's less than or equal to what?
Positive ST.
Exactly. Okay, good. So these are the normal properties of angular momentum that you all have learned. But now, okay, so that's just kind of a quick review. But so we're basically just doing everything we did for normal angular momentum, but now for total angular momentum. But what I haven't told you yet, and what we haven't figured out yet, is how do we construct these total angular momentum states? How do we construct these states, ST, MT? And the way to think about it is, so this is the way to think about it. The easy thing that we've already done is that we have the easy thing that we can do without any hard work at all is we can construct the product states. And we know that for a system of n particles, let's say spin 1/2 particles, let's just use spin 1/2 since that's the easiest one. For n particles of spin 1/2, then we know that we have a set of 2 to the n product states. And we can construct that basis very easily, right? For spin 1/2, you know, we can say, like for two particles, it's going to be like for 2 particles, I can construct that product space very easily. It'll be up, 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 down, down, up, down, down, right? For 2 particles, that's 2 to the 2 equals 4 states. I just constructed them. It's trivial. It's really easy. Product states are easy. Just go blah, blah, blah. You just all the little possibilities. That's easy. But what I want to do now is now I want to convert product states to my total angular momentum eigenstates. And the question is how? You see what I'm saying? Because that's what it means to add angular momentum. It means basically it means to construct these new simultaneous eigenstates of the total angular momentum operators. How do we do that? And that is not obvious. It's not totally obvious. If you think about it for a few minutes, then you will come up with a way to do it. The simplest thing that you might think of after you think about it for a little bit is simply take the operators S total squared, S total Z, and then take all those basis states, all 2 to the n of them, of my product states, and what would you do to find the new eigenstates of these guys? What would you do? What mathematical operation would you do? We know the operators, we know the product states, that's the easy part. How do we get the simultaneous eigenstates? What would we do? Somebody tell me. It's a math question.
The eigenvalue equation.
Of what?
Of each operator.
Exactly. That's exactly right. To find them, you would construct matrices. You would construct S total squared 1, 1, S total squared 1, 2. You know, you would construct the matrices. You would construct the matrices and then you would diagonalize them according to the rules of linear algebra. But the point is that this is the dimensionality of that matrix, it's 2 to the n. So it's quite tedious. So diagonalizing them is quite tedious and it's hard. And nobody wants to do it. You know, nobody likes diagonalizing matrices. Everybody hates doing that. And so, but that's the right way to do it. But we're physicists. And so we like to do things on the cheap, you know, we like to skip the hard math sometimes and find little tricky ways to do things. So So that's the right way to do it. But I'm not going to do that because that's just too tedious. You know, if you had a computer or whatever, you could do it, or Mathematica or MATLAB. But let's do quick and dirty. I want to do it in a quick and dirty way. Quick and dirty. Let's do it the quick and dirty way. So let's just use simple reasoning. We're going to use simple math reasoning. So if you don't understand some of this math reasoning, then you can always, you know, go back to the correct way and just remember in the back of your mind, you know, you can always just diagonalize those operators and that gives you the right answer. But that's just too tedious. And so what we're going to do is we're going to try to use some simple trickery, some simple math reasoning. Okay, we're going to use some math logic. And so let's do some math logic. So what we're going to do, so now I'm going to do sort of like a quick and dirty example. And let's do an example of for finding the total angular momentum eigenstates for and the most important case is 2 spin 1/2 particles. And so I'm going to work through the details for this case, and then we're going to generalize it. And we're going to say that we can generalize this concept for other cases. And so what we'll do then is we will let's do it. And then the idea is that we will generalize this, generalize it. Okay, so for 2 spin 1/2 particles, then the first thing we do is let's construct the product basis. And then we're going to convert it to the total angular momentum basis. So the product basis is, you know that I already did it. There's 2 particles and so we have 2 particles, so it's 2 to the 2. There's going to be 4 states. And I already wrote them down, but I'll write them down again because this is sort of the lingo. The states, the general product state, the general product state can be written like this. It's going to be S1 M1 times S2 M2. But that's too hard to write. Nobody likes to write that. And so the way we write it instead, since these S's never change, they always equals 1/2. So that part is tedious. We don't need to write that. So what we can do instead is we can write it like this. We can write it like we can do it like this. We could write spin up for particle 1 times spin up for particle 2. And then we can, actually, wait, I'm going to write it somewhere else to make it easier to write. I'm going to write it here. So we can write up for particle 1 times up for particle 2 is 1 state. Or we can write it like, or I can say up for particle 1 and down for particle 2 is another state. Or I can write down for particle 1 and up for particle 2. Or I could write down for particle 1 and down for particle 2. So those are the 4 states, the 4 product states. So that's sort of an easier way to write them, but that's still too hard. And so out in the real world, the way that people who know quantum mechanics write this is rather than writing that, that's even too tedious. People are going to write like this, up, up. And it's understood that these things are the same, okay? It's understood that this is particle number 1, the very first one I write, and the very second one I write is particle number 2. That's understood in the notation. So now I'm teaching you a new notation. And it's really trivial, but you have to remember the details or else none of it makes sense. So this state on the left, now I can write it as up, down. But when I write up, down, that's a very special thing. You know, when I write this ket with up, down, that means particle 1 is up and particle 2 is down. And so now this one I can write as down, up. And then this one I can write as down, down. So now I'm going to use this new notation, which is much easier. And that's like what normal people use out in the real world. And so this state up, up has a total M total. And what is the M total? For that state. In other words, yes, say it again.
1.
Exactly, because M total is M1 plus M2. Basically, I'm saying if I hit that state STZ on that state up, up, then that would give me an H bar times some number times that state up, up. And I'm asking for that number, and that number is M1 plus M2, which in this case equals 1. Good. 1. Good. Okay, what is M total for this state?
M1
0.
minus M2.
Say it again, please. I didn't hear. What's M total for this state?
0.
0.
Exactly. What's M total for this state?
It's also 0.
Good, thank you. And what's M total for this last one?
-1.
Exactly. Good. Okay, so I have 4 states, and I know their total, and they are all eigenstates of M total. Yay, that's good. But they are not all diagonalized yet. But let's consider. But now let's do a trick. This is the trick. This is the math trick. Let's notice the trick. The math trick here is always this, the math trick is go to the top. Go to the top, which is M total equals 1. And we notice that there is only one state. Only one state has M total equals to 1. Now, there's only one state, and that state is this state, up, up. And here's the trick. The trick is that I ask myself, I'm going to ask you, is it an eigenstate of these operators, S total squared and S total Z? Is it an eigenstate? And the answer is that it is an eigenstate. And the reasoning, it's like slightly tricky reasoning, because we say, so what we're going to do is we're going to say that this state is equal to the eigenstate S total equals 1 and M total equals 1. But how can I say that? Well, the brute force would be to check. The brute force way would be to check it by hitting it S total squared on this state 1 up, up, and noticing that it equals H bar squared times 1 plus 1 times up, up. That would be the brute force way to do it. But I don't want to do that because that's a lot of work. But you should do that work, as homework. I want you to go through that exercise, and then because then you're going to have to use raising and lowering operators when you go through the algebra, raising and lowering, and you should go through that to see that it works. But now I'm going to try to use clever math reasoning, because what I'm going to say is, let's suppose it's not. Let's suppose it's not. Let's suppose that it was an eigenstate. Suppose its eigenstate S total equals to, say, 2. How can I prove that it's not an eigenstate of S total equals 2? Can anyone guess? Suppose it was an S total equals 2 eigenstate. How can I prove that it's not that?
Professor, could you please explain what you're asking again?
Yeah, it's sort of like a weird math logic. What I'm saying is, look at this state and prove that it's not S total equals 2. How do I know that it's, I want to ask basically the question, so can you show that it's not an S total equals 2 state? Is there a reasoning that you can use to show that it is not S total equals 2?
In our system, I don't think S total equals 2 is possible.
And why is it not possible?
Because we have two particles each with a maximum positive spin of +1/2.
That's right. And another way of looking at it is that if you look at these states, there's no M total equals 2 here. Because if there was an M total equals 2, then we would if I had an S total equals to 2, then I would have to find an M total is equal to 2, 1, 0, minus 1, minus 2. You see what I'm saying? And when we look at the states here, we don't see any of those. And so that tells us that this state cannot be S total equals 2. And now let's suppose it was an S total, a state of S of something lower. So this would be the higher. And then if I said, suppose it was S total equals 0. This is a lower total angular momentum. How can I prove that it's not S total equals 0? Can someone tell me how do I know that this 1,1 state is not S total equals 0?
If it had S total equal to 0, then it could not have M total greater than 0, which it does. So
exactly. So these are not true. And so the only thing that's left is that it's S total equals 1, or I should say the eigenvalue. I should keep my notation consistent. So then the eigenvalue must be S total equals 1. So that's sort of like, you know, tricky math logic, but it's actually correct. So then the S total equals 1. So we've just proven, sort of in a shorthand way, that this state is equal to an eigenstate, the simultaneous eigenstate that I want, of now we see that it's equal to the state 1, 1. See, I've gone from up to now 1, 1, where this is my S total eigenvalue and this is my M total eigenvalue. So that's really nice. So what we've noticed is that the top product state is already an eigenstate of the operators that we want. But how do we get the rest of the eigenstates? How do we get the rest of them?
Can we use lowering operators?
Exactly. Because if we have 1, 1, then we know that S total minus acting on 1, 1 will give me some constant times 1, 0. So then what we have to do then is we have to hit this state 1, 1 with S total minus. And so what we see then is that S total minus is equal to S1 minus plus S2 minus by the definition of the total lowering operator. And so then we have to hit S total minus S1 minus plus S2 minus has to hit the state up, up, where that's the spin of particle number 1, and that's the spin of particle number 2. And that's the rate, that's the lowering operator for particle number 1, and that's the lowering operator for particle number 2. So you have to hit this onto that. And when you do it, you see that this one is going to act on this guy, and this one is going to act on this guy. And so you're going to get some constant times down, up, plus up, down. When you do that, when you hit them, when you hit the lowering operators. And so then if we normalize it correctly, then we normalize it because we know that this has to be some product, some constant times 1, 0. And so when we normalize it, then what we're going to get is 1, 0 is equal to 1 over square root of 2 up, down, plus down, up. Okay, so this is like a tricky way of getting it. And so then by the same reasoning, we can hit it again, same reasoning, then we can hit S total minus onto the 1, 0, and that's going to be proportional to 1 minus 1. And so then, but once you go through the logic, you see that that state is going to be 1 minus 1 is going to be equal to, it's going to be equal to down, down. All right, so now we have these states. We have 3 of them. But we notice that there's, so now we have three S total, M total states. We have 1, 1, 1, 0, 1, minus 1. But we started with how many? How many product states did we start with? Here. How many product states? Exactly, because there's 2 to the 2. So so far we've only found 3 states, so we're missing 1. So we need 1 more. So now we go. So let's go back to this table, and we notice that we have 2 states, 2 M total equals 0 states. But when we did all of our math right now with the lowering operators, how many states have M total equals 0 of these ones that we just discovered? How many?
1.
Exactly. Only 1 state with M total equals 0. And so so there has to be a second one. We need to find a second one. But the thing is, the second state of M total equals 0, then we ask ourselves, if there's a second state with M total equals 0, what would the total spin equal?
0.
Yes, it has to equal 0. And you could do the same reasoning as before. You could say, well, what if, you could say, what if the total spin was 1, or the total spin would be 2? Then there would be more states that don't exist. And because these other states are not there, then these must be false. So that's a way of doing the reasoning. That's like a math reasoning. So then we see that there must be 1 state left, M total equals 0, S total equals 0. And so the way we do it is, a clever way of finding it is to take this state, up, down, plus down, up. And what we can do is we can say, I see that there's 2 basis vectors in there, 2 states. So then we can ask, find an orthogonal state to it. And so you can just kind of look at that and just say, well, I have a two-dimensional, because this is you can think of this in the language of linear algebra, this is a 2-dimensional vector. And so if I had a vector like V that's equal to, say, A plus B, then I could find another vector, I'll call it beta, which is equal to, what's another vector that's going to be orthogonal? You could do A minus B. So it's just using simple linear algebra kind of reasoning. And if these are orthonormal states, A and B. And so then that means that we can find a new orthogonal state, which is 1 over square root of 2 up, down, minus down, up. And then this state is going to be then the 0, 0 state, where this is S total equals 0 and M total equals 0.
Professor, so the reason that the 0, 0 and 1, 0 states are orthogonal is because you can't have a state with both spin 1 and spin, like S equals 1 and S equals 0, right?
Yeah, but I mean, I could even say it differently. I could say the reason that these states are orthogonal is because the eigenstates of Hermitian operators are orthogonal. I can construct an orthonormal basis of the eigenstates. You know, when we talk about the eigenstates of the Hermitian operators, they're always orthogonal. So that's maybe another way of thinking about it. So
right, because we know it's the
states,
other. Yeah, I get it now, I think.
Okay. Yeah, so it's like, it's sort of tricky math reasoning, you know, but and the whole reason why we did this tricky thing is because we wanted to like not have to do that terrible, you know, or diagonalizing of the big matrix. But if you do the diagonalizing of the big matrix, you'll find the same answer. Okay, so now what we've done, so we've done it, and so now we've converted the bases, and so now what we have is the new set of states. And so we have now the total spin eigenstates for 2 spin 1/2 particles. And those eigenstates are as follows. We have, I'll write them here. I have, here they are. We have up, up. I'm sorry, no, I'll write them like this. We have, and remember the eigenstates are S total, M total, that's the notation. And so we have 1, 1 is equal to up, up, because these are the, so here I have the total spin states and here I have the product. I'm writing them in terms of the product basis. And then I have 1, 0 is equal to 1 over square root of 2 up, down, plus down, up. And then I have 1 minus 1 is equal to down, down. And then I have 0, 0 is equal to 1 over square root of 2 up, down, minus down, up. And so that is it. So we've done it. We've added angular momentum, and basically what we've done is we've done a conversion of the basis. We went from the product basis to this new total angular momentum basis, and so this is how you do it. And so I want you to see that these 3 states here are all S total equals 1. And, you know, we have M total is equal to 1, 0, minus 1. And there's 3 of them. And so these states have a name. We call them the triplet states. And that's a convention that people use a lot. So we call these the triplet states. And this state, there's only one, S total equals 0 and M total equals 0. And so there's only one. So we call this state the singlet state. So you hear that notation a lot out in the real world. People will often say, oh, this is a triplet state, or this is a singlet state. And so when they say singlet state, what they mean is that the total angular momentum is 0. But a triplet state means the total angular momentum is 1, because then there can be 3 configurations, you know, 3 M total states. So people often use that language, triplet and singlet. So it's something. So these 3 guys are the triplet, and this guy is the singlet. Okay, so now it's 11 o'clock and I'm gonna go. Remember, I lost 3 minutes because of my technical difficulty. I was on the wrong wireless network. So I'm still gonna use those next 3 minutes to sort of finish this up. And so what I want you to, what I want to do now is to generalize the rule. There's a rule, so now let's generalize this. And when someone says, in this context, when someone generalizes a rule, you know, without proving it, then what you should, the steps that I'm not filling in is that you could do an induction proof. Like you guys all took math, remember how to do those induction proofs. You know, you start with one rule and then you go to the next and then the next. So using a mathematical induction proof, you could prove this rule, but I'm not going to do that because it's quite tedious, you know, and I don't want to do it. It's too much work. But the idea is that, you know, you could do it. And so the general rule is if you want to add two spins, and I'll call them S1 and S2, then the general rule to add them is what you do is, remember, to add two spins really just means to convert. You know, when I say the word add, what I really mean is to convert from the product basis to the total spin basis. That's what it means. Then the rule is this, is that if you have S1 and S2 and you're adding them, then S total can equal S1 plus S2 or S1 minus or plus S2 minus 1 or S1 plus S2 minus 2, on and on and on until you hit S1 minus S2 absolute magnitude. And that's the rule. Those are so this is the general rule. And let's do an example. For example, let's consider Let's consider S1 equals 1. I have a particle that has spin 1. And suppose I have a particle 2 has spin 3. Then I see that for the product states, then we have how many S1 equals 1 states? How many product states does that give me? How many states a particle that has S equals 1? No, one particle that has S equals 1. How many states does that one particle have?
3.
Right, because it could be M total is 1, 0, or minus 1. So this has 3 states, this particle. And if I have S total equals 3, how many states are there?
5.
No.
That's 7, right?
Exactly. 7 states. Because the rule is for S, then it's going to give you 2S plus 1 states. That's the rule. And so that means that the number of product states, so to get the product states, I do basically a tensor product of of these guys and these guys, and that gives me how many states. So how many product states can I make from these two guys?
21?
Yes. 21 product states. Okay, and so I want, you know, you guys can do that, like, and so then now let's use this little rule and let's add the angular momentum, and I have 1 and 3, so the highest total angular momentum is 4, but using this little rule that I have above, it can be 3, 2, and what's the subtraction? 3 minus 1 is 2, so the lowest is 2. So that means I can have total spin 4, 3, or 2. I'm going to write a little ever so slightly different. 4, 3, 2. And now I just want you to see that if I have total angular momentum 4, then how many states is that? How many states?
9.
Exactly. 9 states. If I have total spin of 3, how many states do I have there?
7.
Yes. And how about 2?
5.
That's right. And now if I add these up, 9 plus 7 plus 5, what does that equal?
21.
21 states. So I want you to understand it's the same number of states because it's a basis conversion. And in linear algebra, you know that if I have a vector space and I diagonalize it with one basis set, I get a bunch of states, which is the dimension of the vector space. But if I then convert to another set of basis states, I always have the same dimensionality, same number of states, because it's the same dimensionality. So I'm really stressing this point, you know, to just really drive home this idea that addition of angular momentum is simply a conversion from one set of basis states to another set of basis states, same dimensionality of the spin vector space. Okay, folks, that's a good place to stop now. I'm sorry for going over because I had that technical difficulty. So I'm going to stop the recording. I'm going to stop this and I'm going to start back up again for the office hour. Okay. Bye-bye, folks.
Thank you.
Okay.
Thank you.
Okay.